I'm now recording. Thank you. Okay, so we've talked about, let's talk about what elastic versus inelastic means.
Oh,
Okay, what do you think an elastic collision is?
you go to
Yes, do it again, everybody watch. Okay, that's it. It's a bouncy collision. So a good model of an elastic collision would be a Super Bowl.
Birdie and
Super Bowl. Yeah, so the collision here is elastic. A perfectly elastic collision would be a collision in which all kinetic energy is conserved, right? Compare that to an inelastic collision. Cookie dough. Cookie dough was the inelastic collision, right?
Still haven't calculated that yet.
No, we haven't. Afterward, once we're done with physics, maybe we'll do that.
Real quick.
So we talked about how if we threw cookie dough fast enough, we gave it enough kinetic energy, and it collided with the wall, right? Or we threw cookie dough from both directions, and they collided together. That'd be better, make more cookies.
That's twice the size of a cookie ball.
And so if they came together and they splatted, they don't bounce, right? It splats, and so all that kinetic energy is given up then, right? It's not conserved. The kinetic energy, initial kinetic energy, is lost to heat. And if you throw them fast enough, you cook the cookies, right? So,
Or with your seat.
I'm doubting they're gonna turn out well, but theoretically you could cook it, right? So anyway, so that's inelastic. More often than not, collisions tend to be inelastic. Like if you're in a car wreck, that's inelastic, right? Cars don't typically bounce off of things; they crunch. But they're built. We talked a little bit about this. They're built to new cars are built to crumple so that they give up their energy in a way that's going to be less deleterious to the occupants of the car, right? I mean, the energy is absorbed in parts of the car where people don't sit, right? Okay, so, but what happens now if you're there's some situations where it would be useful to be able to calculate the incoming and outgoing velocities during a collision. Like let's say if you're on CSI Pendleton, you got to be able to make you've got some video evidence that shows, I don't know what the situation could be here, but if you know the ingoing and outgoing velocities of one part of a collision and you need to find the others, or probably more so than in CSI Pendleton, this would be kind of a physics thing. Like if you were, let's say you were, what's an example here? You're looking at a bubble chamber where you're analyzing particles between high energy collisions between elementary particles. And in some cases, certain particles are going to leave tracks in the chamber and certain particles aren't. But you know that there was a collision between two different kinds of particles, one of which you can see its ingoing and outgoing tracks, and the other one which you can't. But you want to know what the parameters were of the other particle. So you've got to do some sleuthing then. Fortunately, in this case, you wouldn't know anything.
I'm trying to research how much energy it takes to bake a cookie.
Well, let's do that later.
Okay.
So we'll want to know then that it's a perfectly elastic collision, and that is elastic in that case. And we want to know what are the incoming and outgoing velocities of the other particle. Well, that would be modeled by a problem like this. Okay, so we'll just do kind of a scaled down version, but you can see where there would be applications where this would be pretty useful to be able to do. So this is going to seem like there's not enough information here, and there wouldn't have been before. But now we've added some additional stuff, and we can do this problem using conservation of kinetic energy, right? If it's elastic. So say we've got a 6 kilogram ball and 12 kilogram ball. The 6 kilogram ball initially travels in the positive x direction with a velocity of 12 meters per second, and has a velocity of negative 12 meters per second relative to the positive x direction after the collision. So that's all we know. All we know is that before we've got this ball coming in, 6 kilogram ball coming in at 12 meters per second, and afterwards it's outgoing at 12 meters per second in this direction, right? We don't know anything about the initial or final velocities of the 12 kilogram ball that it hits, because let's just say this is the setup. We've got a curtain up here, and you can just see that this ball, right as it leaves your view, it collides with the other ball and bounces back. Based on just that data, though, you should be able to tell me what was the initial velocity and final velocity of the hidden ball that it bounces off of. Okay. How in the world could we do that? Any ideas?
Probably not.
What do we know about the situation?
Can you do that if you don't have the mass of the other ball?
No,
So you need to
you
have
can't.
mass.
You could do it in terms of the mass of the other ball, which would be kind of interesting. That's good, oh, that's a good thought for a problem there. You could do it in terms of m, the mass of the other ball, but the velocities would be dependent on whatever the mass was, you know, okay? What are some things you know about this, though? How many in the system, how many objects are there in the system? Two, okay. So what can you tell me about the system as a whole?
5.
It's equal or. I guess we can cancel some.
Okay, there's gonna be some things that maybe do remain equal before and after. What do we call that? Some quantities maybe.
Well, the mass remains equal before now.
Okay, so mass, we say mass is conserved. True. That's not helping us much, but that's true. We always want to look in physics when we start doing harder problems. So like as you move further on in physics, we always want to appeal to conservation laws whenever we can. Are there any quantities that are going to be conserved?
Energy.
Energy is, because it's a perfectly elastic collision. What is always conserved in a collision? Momentum. Good, right? Momentum is always conserved, right? Momentum, unless there are external forces acting, and there aren't in this case, right? So we could set up then a system of equations here because we know that the momentum is conserved and so is the energy, right? So let's start off by using, how about conservation of momentum?
Thank you.
Okay. So momentum what's the momentum before the collision? Well, what's the momentum of the incoming ball?
6.
6 times
12.
12. The velocity's positive 12. We'll just suppress all the units, right? They're in standard units. So we end up with 6 times 12 plus, what's the momentum of the other ball?
6 times, no,
Negative
12
Times-
12. Negative 12. 12
Uh,
times 12.
Well, no, it's 12, right? 12 is the mass. Momentum is just mass times velocity, right? So it's gotta be 12 times, who knows? It's unknown, right? So we'll just call it initial velocity,
So X,
right? Everybody agree? You don't know what it is, it's an unknown. What's the momentum afterwards? It's gotta be the same, the total momentum's the same. What's the momentum of the first ball afterwards?
72.
6 times 12, no. Negative 12,
Negative 12.
because momentum is a vector quantity, right? The velocity is a vector quantity, so it's 6 times negative 12 plus, what are we gonna call the momentum of the other ball? It's gonna be the product of, its mass stays the same, thanks to River, we know that, right?
Yep.
Okay. What do we call its velocity afterwards?
V final.
V final, how about it? I like that. Okay, so there's one equation. How many unknowns are there in that equation?
2.
Okay, so let's think about this algebraically for a second. Okay, we got these two unknowns. How many unique equations do we need to solve a system involving two unknowns? 2, so we need another equation, but we got that. We got that because we also know that energy is conserved. Now, is kinetic energy a vector quantity?
No.
It's not. It's not. So that's even easier to work with, right? So let's use conservation of kinetic energy here, okay? So what's the kinetic energy of the ball initially? 1/2 times
6.
mass, right? So 1/2 times 6 times 12 squared. So what do we get there? 3 times 144, 288, what's that gonna be? 432, is that right?
144 times 3.
4, isn't that right?
Yeah.
Somebody,
Yeah, it is.
it is right? Okay. So plus,
432.
what about this one?
1/2 times 12 times V
Times V naught.
squared.
I'm not gonna put a vector hat on it though, because this time we're just talking about speed, right?
Why?
equals,
I'll put that.
right, because remember, it's just speed, kinetic energy is 1/2 mv squared, where v is the speed, not the velocity. Okay. It's not a vector quantity, and over here we end up with 1/2 times 6 times -12 squared, right? Okay, now, plus 1/2 times 12 times final speed squared. Well, I don't even really need to calculate the 1/2 times 6 times 12 squared, do I? How come?
Do the same.
It's the same on both sides, so what could I do? Cancel, right? So I could just do that. Okay. So that means we end up with 1/2 times 12 times v naught squared equals 1/2 times 12 times v final. Let's just divide each side through by 6. What do we end up with? Pretty
They
simple.
go the same.
We end up with v naught squared equals v final squared, right? So the speeds are the same, okay? Incoming and outgoing, they have to be the same. So now all we've got to do is just solve the system, right? So what can we do up here? Let's take this first equation. So that's, what is that, 72, I used the right speeds, didn't I?
Yeah.
Yeah, 12, okay. So we end up with 72, and that's a minus 72, right? And so let's go ahead and let's combine those on one side, right? So the yellow equation,
144.
we could write that as 144 equals, and I'll subtract this over to this side, right?
Whoa,
How's it
what?
less zero?
That'd be a 0, good sir.
No, because
you're
that's
adding
negative
negative.
72
Oh,
and
you're
72.
Bruh, the smarter
So
people.
I'm gonna add 72 to both sides.
Oh, yeah, okay.
And so then over here, we've got 12.
Smarter than
Actually, it's -44.
Right? Divide each side through by 12, how about?
I know what that is, it's 12.
And we get 12 equals v final minus v naught, right? And so let's go ahead and just arbitrarily, let's solve this for v final. Not that it makes any difference.
Equals 12 plus.
Yeah, 12 plus v naught, right? Well, now look at this. We've got a pretty simple system to solve now, right? We'll just make a substitution. Okay, we'll just say,
Put in
let's go ahead and
12 plus
square
V.
this out and plug it in for v final, and we'll just solve the equation, right? So what's that give us? Then we end up
144 plus
getting,
V naught squared.
what's the combination of yellow and green is? Nothing, I guess.
Yeah.
It can't be that tricky. It's gonna be, we're going blue. So then when we combine those, we're gonna get v final squared, so 12 plus v naught squared equals v naught squared, right? There's v final squared, everybody agree? Right? Okay. So if we square that out, what is this if I expand it? V naught squared plus,
144.
no, but I have to do more than that, right? 24 v naught
Oh, yeah, okay.
plus 144 equals v naught squared. What can I do now?
Take out the V naught squared.
Good, I could subtract v naught squared from both sides and get 24 v naught equal, actually, hang on, 24 v naught
Equals -1.
minus 144 equals 0, right? I mean, I could just put it, why don't we just do that? We'll just do that.
Why'd you switch this?
Yeah, I don't need to, we'll just do that.
To negative?
Where?
Why'd you switch the sign to negative on 144? Wouldn't it be -144?
Yeah, but I'm gonna subtract, oh, hang on. Yeah, you're right.
Yeah.
Yep,
Equals negative.
you're right.
Okay, that was,
It is negative, you're right.
No, it's just 6, v naught equals -6.
Right, so if I divide by 24, v naught equals -6. So what's v final?
-6,
No.
why not?
6.
Ah, okay, so,
Ripples.
okay, so coming into the collision, the other object was traveling in the negative x direction. Yeah, didn't it work? So it was going like this, right? Other way around, it's kind of going like that, right?
That's good.
Yeah. Does that make sense? Say it again?
Can't you just use the ratio of the weight to find that then?
Well, no, because what if, I mean, this one worked out to be symmetrical.
You
The-
couldn't use the momentum though, right?
Well, yeah, but you have to use them both. What if this worked out pretty nicely because this was symmetrical, 12 and negative 12. But what if that was negative 9? Gets a little trickier.
Yeah.
Okay. Yeah, then it wouldn't hold. Okay, make sense? So we can do it.
Yeah, that makes sense that the ball went twice as much as its mass,
Mm-hmm.
and then the other ball went twice or half as much as its
Mhm.
loss.
That's wrong.
At least.
Right? Okay. I think we're good. Let you guys work. I'm gonna give you, yeah, seriously, that's it. I'm gonna give you, that's the last thing that I wanted to talk about was just a little bit of, just an example of a perfectly elastic collision, and then we're good.
So the velocity is positive after, the velocity of the ball after the collision is positive.
So, well, which ball are you talking about?
Well, the answer.
The answer, right. So the 12 kilogram ball was negative to begin with and rebounded positive.
Oh, so that one would be positive, and so the after would be negative.
Yep.
So negative 6.
Yep.
And then what would units be? Oh, meters per second.
Mm-hmm. All right. That's good. So I'll let you work